So good morning, ladies and gentlemen, and welcome to today's training. This morning we begin with the training on BGP principles and configuration. BGP principles and configuration. Now, so far we've looked at many protocols that are used to share routing information within an autonomous system. Now, such protocols that are used to propagate and enable the sharing of routing information within an autonomous system are called interior gateway protocols, IGP. So they're called IGP. Interior gateway protocol. Now, so far we've looked at, okay, we have examples like RIP, OSPF, and recently we also looked into ISIS. So these are IGPs. Now we also have exterior, EGP, exterior gateway protocol. One of the examples of an exterior gateway protocol is BGP. And as we are going to see, actually, we had a protocol called EGP. But now, there are things it could not do, and therefore BGP replaced EGP. But BGP is still thought of as an exterior gateway protocol. So we want to look at that in this topic and understand how BGP operates. Well, when you talk of exterior, we are talking of sharing the routing information between autonomous systems. So that is what we want to understand in this particular topic. Okay, so I'll read the forward. So an autonomous system, AS, is introduced into the exterior gateway protocol, EGP. So an autonomous system is a set of routers under a single technical administration, and all the routers in an autonomous system use the same routing policy. So an IGP is used within an autonomous system to calculate and discover routes. So routers within the same autonomous system trust each other. So IGP route calculation and information flooding are completely open and require little manual intervention, as we saw with both OSPF and ISIS. Neighbors can be formed automatically, can be discovered and established automatically, and routes can also be shared. But it's a little bit different when it comes to BGP. Now, inter autonomous system connection requirements promote the development of an exterior gateway protocol. Now, BGP is an EGP and is used to control routes and select. So control routes and also select optimal routes between autonomous systems. So generally, that's the forward. Now, let's go to the objectives. Oh, what is not happening? Okay. So upon completion of this section, you'll be able to. Winnie, please kick us off this morning.
Upon completion of this section, you will be able to understand BGP principles, master BGP attributes and applications,
yes,
and be familiar with BGP route aggregation applications.
Exactly. Okay, so let's begin with an overview of BGP. Now, as I mentioned earlier, BGP is a predecessor. No. BGP is, how can I call it? When you talk of predecessor, what do we mean? Which one comes before the other? So BGP is the predecessor of EGP. I don't know whether that is correct. The one that comes after, is it the predecessor? Which one is the predecessor of the other here? On this statement, BGP is the predecessor of EGP. Is this statement correct? If BGP is the one that replaced EGP, is that statement correct? The way I've written it?
Yes, sir.
Correct, eh?
BGP, yes, sir.
Okay, okay. So BGP is the predecessor of EGP. Now, EGP is an exterior gateway protocol that was used to share routes between autonomous systems. You see, for example, here, we have autonomous system that has that number there. Sorry, my mouse is misbehaving. We have another autonomous system there. We have another one here. We have another one here, like that. So within an autonomous system, routers share routing information using IGPs such as OSPF and ISIS. Between autonomous systems, we configure BGP to share routes. So that's why we are saying here that BGP is used between autonomous systems to transmit and control routes. Now, why did BGP replace EGP? So let's look at problems with EGP. Now, EGP had two main problems. Number one, could not select optimal routes. So as we are going to learn with BGP, you can actually be able to configure attributes so that packets can follow optimal paths to their destination. So that was one of the problems with BGP. Number two, also EGP could not prevent what we call routing loops. We are going to see several strategies that BGP uses. BGP uses. So really, of course, these advantages are what forms the merits for BGP. Now, other than those two, that BGP can select optimal routes, can prevent loops, BGP can also discover. They can discover and establish neighbor relationships. So that's the other advantage of BGP, other than the two that we've listed up there. And number two, BGP also provides what we call route control capabilities between autonomous systems which are not fully trusted. Because between autonomous systems, you're now talking of interconnecting Airtel, KenNet, and Safaricom. So this is what you're calling autonomous system. You're interconnecting all those ISPs, and they don't fully trust each other on the internet. So BGP has ways of configuring route control, and we're also going to see that in a short while. Now, on the internet, most of the ISPs or an autonomous system is uniquely identified by what we call an AS number. So this is a unique number that uniquely identifies an autonomous system on the internet. on the internet. Now, autonomous numbers, just like many other internet numbers, are managed and assigned by IANA, Internet Assigned Numbers Authority. Now, we have two types of autonomous system numbers, AS numbers. The first one was what we call the 2-byte, the 2-byte AS numbers. They ranged from 1 all the way to 64,511. Then from around January 2009, they also extended the size of an autonomous system number, and they started using 4-byte autonomous system number. So a 4-byte, if you do 4 raised to power 32, it begins from 65,535 all the way to around slightly below 3.4 billion. So it gives you all those numbers. So earlier systems were identified with 2-bytes. Autonomous system were identified by 2-bytes autonomous system number, but right now most of the autonomous system, newly established autonomous system, are being given a 4-byte autonomous system number. So as you can see here, for example, this one is using 65,000, 65,001, blah blah blah. So these are what we are calling the AS number. Those are what we call the AS number, and they are used to identify autonomous systems, uniquely identify autonomous systems. Okay, so now let's look at the BGP characteristics. So in the figure, 2 BGP routers can establish neighbor relationships across multiple routers. Now, as we are going to see, BGP establishes connections using TCP. So BGP established connections between routers using TCP. TCP, so that we can verify that indeed the connection is up, and so that it can guarantee reliability before we begin sharing information. So that's one of the things. Number two, they're saying they can also establish neighbor relationships across multiple routers, as we are going to see. So for example here, this router here has been able to form a BGP relationship with this router here via this and this router, because they are not directly connected, but they have established a BGP relationship. So we're also going to see that we can establish BGP relationships between routers that are on different autonomous systems, like what we are having here and what we are having here between this router and this router. But we can also establish BGP relationships within an autonomous system, and we are going to see what that is called. So to implement on-demand route control selection, various BGP attributes are designed and carried in routes. So we are going to go through a number of BGP routes that are actually carried in the update message of the BGP packet. So let's see how is the neighbor relationship? How is the neighbor relationship established in BGP? Now, BGP relies on TCP. BGP relies on TCP, and therefore, before the neighbor relationship is established, they have to go through the TCP three-way handshake. So send a SYN, send an ACK plus a SYN, then send an acknowledgement. We already understand how that particular process actually works. So I've explained that the reason as to why we are using TCP is to ensure reliability, because the interconnection between autonomous system most of the time uses one links that are unpredictable, and sometimes they can go down due to either link congestion or physical problems or something, and they can lead to packet loss. So we don't want to share routes to a router that is not up. So that's why we have to ensure that we've connected through TCP. Now, in particular, BGP routers listen for TCP requests on TCP well-known port 179. 179. 179. Now, the other thing that you need to understand is that unlike the IGPs that we've looked at so far, like OSPF and ISIS, which establish neighbor relationships or discover neighbors in multicast mode, with BGP, neighbor relationships are discovered in unicast mode. So what we're saying is that, for example, OSPF discovers neighbors in multicast mode. What does that mean? Multicast. Why did I write it like that? Multimedia. Multicast mode. What this means is when a router wants to discover and establish neighbor relationships, it will send the hello packet to a multicast destination address, so that any other router that has been configured with OSPF will receive and process that hello packet. But when it comes to neighbor discovery and establishment in BGP, it uses unicast mode, meaning that it will send a packet, a hello packet, to a specific device on the internet. Because with BGP, we don't trust each other, so you must be knowing me for you to send a request to me. Now, because they're done in neighbor discovery is done in unicast mode, then neighbors, BGP neighbors must be manually specified. So BGP neighbors must be manually specified using the peer command, as we are going to see. Okay, so let's move on and now look at the process of okay, now let's look at the neighbor relationships. Let's look at the neighbor relationships in BGP. Now we have two neighbor types. So BGP neighbor types. Number one is called EBGP. Number two is called IBGP. Generally, EBGP ni neighbor relationships between routers on different autonomous systems, while IBGP is between routers in the same autonomous system. So we are going to see why. Why do we need to specify IBGP? So as you can see, RTD here is in AS200, RTE AS300, and we have AS100 here, which has three routers, RTA, RTB, and RTC. We can see that in AS100, they are using the IGP OSPF. Now, if RTB was to establish a BGP neighbor relationship with AS200, then that neighbor relationship is known as EBGP, or Exterior Border Gateway Protocol. So similarly here, we are forming a EBGP relationship. Now, the problem is that now how can the internal routers in this particular autonomous system AS100 how can they be able to learn about the routes in AS200 and in AS300? How can these internal routers in AS100 be able to learn the routes from AS200 and AS300? Now, one way to do that is to import the BGP routes into OSPF. The same way we've been importing routes. So we can import BGP routes into AS100. And therefore, all the routes that have been learned through BGP from this AS and this AS are going to be installed in AS100. Now, that has a problem. That has a problem because autonomous systems most of the time have very many routes. And therefore, if you want to import all the routes from one autonomous system to another, to the IGP, really the IGP cannot be able to support all these routes. So that's the problem, problem number one. Problem number two is that BGP carry, so problem number one, we've said too many routes. So IGP cannot support. IGP cannot support these routes. Now, number two, BGP routes. BGP route attributes are lost. BGP route attributes are lost when you import BGP routes into IGP. So we are going to see why attributes are important. But for now, just know that if we import BGP routes into IGP, then the attributes will be lost. Then also BGP requires strict control. And therefore, if you import BGP routes into IGP, it actually complicates the configuration and the maintenance. The configuration and the maintenance of the network. So these are some of the reasons as to why you cannot just import BGP routes into your IGP. However, to overcome these advantages, BGP needs to be designed in a way that it can allow the transmission of routes within an autonomous system. So how is that achieved? That is achieved through the second type of neighbor relationship, which is called IBGP, or Interior Gateway Protocol, Border Gateway Protocol. So what that means is this. That routers in the same autonomous system can establish IBGP neighbor relationships. So what that means is this, that RTC and RTB can form IBGP neighbor relationship. RTB and RTA can form IBGP. And therefore, once we have IBGP neighbor relationships within the autonomous system, they can have in their table routes that have been learned through EBGP. They'll have these routes without necessarily having to install those routes in your IGP. So that is what we call IBGP. So we have those two types of neighbors, EBGP and IBGP. Okay, so let's see. We've said that neighbor relationships are established using using the unicast mode, and therefore you have to manually specify this particular. You have to manually specify these particular routers. So in this example, let's look at how we can configure an EGP neighbor relationship between RTE, that is in AS300, and RTC, that is in AS100. So just like in OSPF, you need to configure a router ID in order to uniquely identify, the router. So router ID 5.5.5, the rules still remain. If you've not specified the router ID manually, it will go for the highest IP address among all loopback interfaces. If you've not configured any IP address on a loopback interface, then it goes for the highest IP address among the physical interfaces. So that rule still remains. Now, other than the router ID, the next thing you have to configure is the AS number that router is in. So you do that by using the command BGP, then you specify the autonomous system number. So BGP 100, because this router is in AS 100. BGP 300, because this router is in AS 300. Okay, now after that, you need to now specify the neighbor using the peer command, So you do peer, then the next thing that follows is the IP address. The IP address of the directly connected interface of your neighbor. So for example, 10.1.35.3, which is the IP address of this physical interface. Then after that, you do the command AS number, then 100. You specify the AS number that this peer is in. So this is the S number of this peer. This peer is in AS 100. So similarly here, we are establishing an EBGP peer relationship here with this particular interface on RTE. So peer 10.1.35.5. So this guy, .5. Then this guy is in AS 300. This guy is in AS 300. So that is how you establish an EBGP peer relationship. Now, other than that, you can also establish IBGP. So RTB and RTC are in the same autonomous system. So they can establish an IBGP peer relationship, neighbor relationship. So how to do that? You do peer, then the physical IP address of this particular interface that you want to peer on RTB. Now, you notice that RTC and RTB are not directly connected. They have been connected through RTA. So this is the other powerful thing about BGP, because BGP, unlike OSPF that has to establish neighbor relationships hop by hop, router by router, BGP can actually establish neighbor relationships through other routers because it uses TCP. So as long as that guy is reachable, then we can establish a neighbor relationship. Now, when the AS number is the same as mine, when the AS number is the same as the AS that I'm in, so when the AS number matches, what neighbor relationship do we establish? We establish an IBGP neighbor relationship. So generally, that is how we manually establish neighbor relationships in BGP. As we've said, you can establish EBGP or IBGP. EBGP if you're on different autonomous systems. IBGP if you are within the same autonomous system. Now, okay. Now, most of the time, it is recommended that when you're establishing EBGP, neighbor relationships, you establish them through the directly connected physical interfaces on the two routers. So you can actually confirm that through this. You can see here, we are using the physical interface. Sorry. You can see that we're using the physical interface on RTC.3 there. On this side, on RTC, we're also using the physical interface .5, this one. So you use physical interfaces. You use physical interfaces when you are establishing EBGP, neighbor relationships. Now, on the other hand, it is recommended that when you're establishing IBGP, neighbor relationship, you use loopback. You use loopback interfaces. You use loopback interfaces. Now let's see. We want to peer to RTB. So the command is this. So first we do peer 2.2.2.2.2 AS number 100. Here 2.2.2.2 is the router ID of RTB. So this is the router ID, 2.2.2. Then now here we do the next line now, the next command will be peer 2.2.2.2 connect interface loopback 0. So what that really means is we are peering through loopback 0 and via loopback 0. So generally, that is what is recommended. The reason as to why we do or establish IBGP neighbor relationships via the loopback interface is because the loopback interface is always up after being enabled. So it can rarely have any issues, and it will always be reachable through your IGP most of the time. So establishing IBGP neighbor relationships through loopback interfaces is more reliable because the interface will always be up and it will rarely encounter any issues. And that particular loopback interface is reachable within your autonomous system because you have an IGP. So I hope that is clear. Any questions so far? Any question or comment? Okay. So after we've done that, let's look at the neighbor relationship establishment. So we have a number of steps that the neighbor relationship between two routers undergo before they become neighbors. Now, before we begin establishing neighbor relationships, we have to go through the TCP connection, three-way handshake. So before we establish TCP, connection, we're in an idle state, an idle state. After we have established a TCP connection, then our state changes from idle to active state. Now, it's on the active state that you can actually send the first BGP message. Now, let me talk about the BGP messages. Now, generally, okay. So BGP messages. So as you can see here, we have a message called open. You can also see another one called keep alive. We also have another one called update. They're actually updates. Then you have another one called route refresh. And lastly, we have a message called notification message. So as you can see, we have 5 messages that are used with BGP. So let's begin with the first one here, the open. The open message. Now the open message is used to establish. Let me just drag this. Sorry. The open message is used to establish a BGP connection between neighbors. A BGP connection between neighbors. It is only sent after the TCP connection is up. Now the keep alive message is used to confirm and retain their connection. When you do the lab, you'll see that the keep alive message is normally sent after every 90 seconds by default. Then you have the update message. Now update message is actually what is used to exchange routing information. Generally, in exchanging routing information, it does 2 things: advertise and withdraw. Withdraw routes. So routes that are reachable are advertised. If I had advertised a route and it becomes unreachable, I send an update message to withdraw that route. So I simply specify the network address. Hey, this network has gone down. So delete that particular route from your BGP routing table. Then you have route refresh. Route refresh is used to request route refresh. This is when a requests a neighbor. You request a neighbor to send routing information again after your routing policy changes. So when you want another person to resend their routing information, then you send a route refresh. Then notification is for error. Error. Error alert, let me call it that. So when an error occurs within your BGP network, then that is what is going to be sent. Okay, so let's move on and now look at the open. So when you send an open message, my mouse. When you send an open message, you move from the active state to the open sent state. Open sent. Now, when you're sending an open message to establish the BGP connection, there are a number of parameters that you send. For example, the AS that you are in, so your AS number, you also send the authentication details and so on and so forth. So if if all the parameters are matched and they're good, then you transit from the open send state to open confirm. So this guy has also transited to open confirm, and it's only after you're in open confirm that now you can be able to send your first keep alive packet. So when this guy receives your keep alive packet, they transit to the established state. And now it is in the established state that they can be able to send all the other messages, including update, keep alive, route refresh, and notification messages. So generally, that is how the neighbor relationship is established, and those are the 5 BGP messages. Any question or comment before we move on? Okay. So now let's look at BGP route generation modes. So how does BGP share route information? Now, BGP has 2. BGP has 2 route generation modes. So the first one is using the network command. Number 2 is using the import command. Using the network command or using the network command or using the import command. So let's begin with the network command. So the network command imports existing routes in an IP routing table into BGP routing table one by one. So let's look at this particular scenario. Now, in this scenario, RTB has a directly connected network. This network here. So this is a directly connected network. It interconnects it with RTA. Now, RTB has also learned through OSPF about this network here, the 1.0 network. Now, in RTB, we have also configured a static route to this network that is interconnected to RTA, the 100.0.0.0 network. So this one is a direct route. This one is a static route. This one learned through OSPF. This one is a direct route. Now, RTB can advertise all these networks to its EBGP peer by using the network command like this. So we specify the router ID, then we go ahead, BGP 100, then peer. So we are peering to RTC. We are peering to RTC on this particular interface here. So after that, we use network. So network 10.1.12.0, then the mask 255.255.255.0. Similarly, we also advertise the 100.0.0 and the 100.0.1.0 networks. So that is how we advertise routes to our neighbors using the network command. Now let's see how will this guy now see it. Now see, in RTB, if we do display IP routing table, we will see that the 12.0 network is a direct route. We will see that the 100.0.0.0 has been statically configured. So you can see from the protocol there. And you can see that this network, the 100.0.1.0 network, was learned through OSPF. Now, in RTC, we've advertised all these networks to RTC using BGP. So in RTC, if we use the command display BGP routing table, we can see that indeed we have those three networks. We have those three networks, and if we want to go to any of these networks, our next hop is this interface on the BGP neighbor RTB. So in a short while, we're also going to look at some of these other fields and understand what they mean. Okay, so that is how you use the network command. Now let's go to the import. The import. Now, as you might already have guessed, with the import command imports routes into a BGP routing table based on the running routing protocol. So the import command can import routes from RIP, from OSPF, from IS. It can also import direct routes, and it can also import static routes. So the scenario is very similar here. So this is a directly connected network to RTB. This one has been learned through static configuration, and this one has been learned through OSPF. So here we configure the neighbor, the peering between RTC and RTB using those commands that we've seen there. Then after that, we use the import. We use the import command. Now you see here, we are saying import route direct. Import route direct. So that's how we import directly connected routes. Then import route static. This is how we import statically configured routes into BGP. Then import route OSPF1. So we want to import routes that have been learned through OSPF process 1. So that's how we do it. Now, in order to prevent routes from being imported into BGP, all other routes from being imported into BGP, for example, all other routes that have been learned through OSPF1, we can configure what we call a routing policy, a topic that we are going to look at a little bit later. Now, in this particular routing policy, we want to apply what we call an IP prefix on the import direction. Now, this is what we call an IP prefix. An IP prefix is very simple. It's simply used to identify packets from a particular network, just like an ACL. So for example, IP, then IP prefix, then the name of that IP prefix, we are calling it import, then index 10. Then we want to permit packets from this network having this mask, like that. So similarly, we are selecting packets from the 100.0.0 and packets from that particular network. Then we come and say route policy import permit node 10 if match. So it is this route policy that we are applying here. So we're not going to import all the direct routes. We're only going to import a direct route if it matches, if it has been permitted in our routing policy. So we are going to learn about IP prefix and routing policy much later. But at this point, just know that here we are just trying to reduce the number of routes that are going to be shared to RTC by using the import routes policy there, the route policy and IP prefix. Okay, so let's move on. So if you look at the routing table for RTB, indeed we have the 3 routes. So for RTB, we have the 3 routes that have been learned through direct, static, and OSPF. And if you look at the BGP table for RTC, display BGP routing table, you can actually see that we've advertised those 3 routes using EBGP, using BGP generally. And this time we use the import command and not the network command. So those are the 2 ways in which you can advertise routes to your BGP neighbors. Now let's look at BGP route advertisement rules and route processing. Okay. Now let's go through this. BGP routes are generated in either network or import mode. We've already seen that. Now they are encapsulated in update messages. We already saw the update message. So they are sent. These routes that are advertised are sent through update messages and advertised to the neighbors. Now, BGP advertises routing information only after a neighbor relationship is established. So we said that it's only after sending the open messages and you're on the established state that you can be able to send the update messages. Now, update messages are used to advertise reachable routes and also withdraw unreachable routes. Now, an update message contains a number of information. The first one is what we call the network reachability information. Network layer reachability information is simply the network address, which they normally call the IP prefix, and the hello guys, I'm sorry, my internet encountered an issue there. Can you hear me?
Yes, I can.
Nilipotelea wapi? Are you still able to see my screen? Hello?
Yes, I can see it now.
Oh, you
Yes, I can
see
see it now.
where exactly did I? Where was
BGP
I?
update message.
Where?
The BGP message.
Hapo sasa.
Okay. Okay. So we've said update message used for 2 things: advertise reachable routes and withdraw unreachable routes. The message contains the network layer reachability information, which is simply the network address, commonly referred to as IP prefix, and the mask, commonly referred to as the prefix length. So there's nothing to fear there. It also carries the path attributes. The path attribute is used to detect and prevent loops, and also to control optimal route selection, as we are going to see. So path attribute generally is the path that this particular update message has passed through, the autonomous systems that it has been able to pass through. So maybe it has been advertised from S100 to 200, then 300, then 400. So we are going to see that in a short while. Then also it can carry withdrawn routes. So withdrawn routes, again, it's simply going to carry the network address and the mask of the unreachable route that is supposed to be withdrawn. Now, BGP route advertisement must follow specific rules in order to prevent potential problems. So let's look at the very first rule. Now, the very first rule states that you only advertise the optimal route. You only advertise the optimal route to the neighbors. To the neighbors. Now, in this example, RTA is connected to a network segment 100.0.0.0/24. Now, RTD can learn about this network that is connected to RTA via RTB or RTC, because RTA will advertise to RTB via EBGP and also to RTC via EBGP. Then these two, RTB will advertise using IBGP and using IBGP to this guy. So you can see that RTD can learn. RTD can learn about this network. It will learn from this guy and from this guy. Now, which one is it going to advertise to RTE? Is it going to advertise the one that has been learned through RTB or the one that has been learned through RTC? Now, if we look at the BGP routing table for RTD, display BGP routing table, we can see that indeed the network 100.0.0.0 has two different next hops. So we have this one here, 12.1, and we also have 13.1. So 12.1 simply means it has learned it through RTB, because RTB is the one that has been connected via 1.2. 13.1 means it has learned that route via RTC, because RTC is the one that is interconnected via that particular network 1.3. So I hope that is clear. So which one among the two should it advertise to RTE? Now, if we go to RTE and do display BGP routing table, we can see that it has only advertised a single. It has only advertised a single route, which is now what we are referring to as the optimal, route. Now, how does it know which one is optimal? It looks at a number of parameters which we are going to look at shortly. But in the meantime, let me describe a number of things that are on the BGP routing table. So fields on the BGP routing table. Fields on the BGP routing table. Where should I put this one now? Okay, maybe I can put it there. Okay. Now, the first field is called the status code. Now, the status code has a sign, that particular sign, which means that the route is valid. Let me use a hyphen. So this means the route is valid. Then we have the greater than symbol. It means that this route is the best. We are going to also see an I, which means that we learned this route from internal. We're also going to see an S, lowercase s, which is going to mean that this route has been suppressed. You're going to see what suppressed means in a short while. And we have two others that have left out, D and uppercase S, which you can look at later. Now, the status code, look here at these ones here. So you see, where am I going to put this so you can see it? Okay, good. Okay, so you can see here we have a star. So we have a star. Star means that that route is valid. Valid means that that route is reachable. That route is reachable. This next hop is reachable, generally. So that is what that means. Now, greater than as you can see here, greater than means that that route is the best. So you can see this one here that has the next hop of 13.1 does not have a greater than. It just has a star and an I, a star and an I. So it's not the best, and therefore it's not the optimal. It's not the optimal route. So the one that will be advertised is the one with this next hop, 12.1. So best. Then I means that it was learned internally before being shared. Suppressed, we are going to see that in the coming slides. Okay, so let's move on and look at some of the other fields. So the other fields include what you call the origin. The origin. So you can see here we have OGN. OGN. That is what we call the origin. The origin. Now the origin can have several indicators. An I, meaning that that route was learned using an IGP, and we're going to look into that shortly. Then E, meaning it was learned through an exterior gateway protocol, EGP. Then we also have question mark, which means it's incomplete. So I'm going to explain I, E, and incomplete in a short while. Then we also have other fields like the network. The network field simply is used to specify the network that has been advertised, the network address. Next hop is the next hop towards the destination. So the IP address of the next hop. MED, multi-exit discriminator, we are going to look at it in depth in the coming slides. Simply used to give the route metric. Local preference, we're also going to look at that in depth. Preference value, and lastly, we also have the path. So preference value, we're also going to look at that. It is Huawei specific. And then we have the path. The path is the AS path. The AS path. Now, for example, we're also going to look at that. For example, this network 100. Let me just clear everything. This network 100 has been advertised from AS 100. Now, when it's advertised to the next AS, the path is noted that, hey, I've come from AS 200. Now, when it enters AS 200 and RTD advertises it to RTE, which is in AS 300, it also adds on the path that, hey, this guy has also passed through AS 200, like that. So you can know that this particular route came from AS 100, then 200, and if this guy was advertising it to another, then 300 will have been added here. To another AS, then 300 will have been added there. So that is what the path is, and we're going to know what it means in a short while. So in rule number 1, only the optimal route is advertised to the neighbors. Now let's look at rule number 2. So rule number 2, advertise the optimal route obtained through EBGP to all BGP neighbors. Now what that means is that a BGP router advertises the optimal route obtained through EBGP to all BGP neighbors. So advertise EBGP to BGP neighbors. What that means is advertise routes that have been learned to EBGP and IBGP neighbors. So advertise routes that have been learned from another autonomous system. You can advertise them to other autonomous systems, or you can also advertise it within your autonomous system. So that is what this rule means. That is what this rule means. So let's look at this example. So we have a network here, 100.0.0 connected to RTA, which is in AS100. So RTA will advertise it to RTB via EBGP. Now, RTB will advertise it to RTD using EBGP. And that's why if in RTD we do display IP routing table, we are going to get the entry for that network. On the other hand, RTB will also advertise the 100.0.0.0 network to IBGP. How does it do that? Using IBGP, and that's why in RTC, again, if we do display IP routing table, we are going to get the 100.0.0.0 network. So this rule simply says a route that has been learned through EBGP can be advertised to other autonomous systems or to other routers within your autonomous system. That is what RTB has done. So advertise the optimal route obtained through EBGP to all BGP neighbors. We have two types of BGP neighbors, EBGP and IBGP. Okay, so that is rule number 2. Let's move on and look at rule number 3. So what does rule number 3 say? Do not advertise optimal route that has been obtained through IBGP to other IBGP neighbors. So what does this say? No advertise IBGP to IBGP. Don't advertise will be a better word. Don't advertise. Don't advertise IBGP to IBGP. Don't advertise IBGP to IBGP. Okay. Now, what we are saying here is simple. What we are saying here is simple. This guy, RTA, has a network 100.0.0.0. Now, all these routers, RTA, RTB, RTC, are in AS100. Now, router A advertises that network to RTB via IBGP. It also advertises that route 100.0.0 to RTC via IBGP. So that's why in RTC, for example, if you do display BGP routing table, you can see that the 100.0.0.0 network is installed in the BGP routing table because it has been advertised through IBGP. Okay, now what happens is this. The reason as to why we do this, you cannot advertise a route learned through IBGP to other IBGP neighbors. The reason as to why we put this rule is to prevent loops. That's the main reason, to prevent loops. Because if this one advertised to this one 100 and also advertised to this guy, then when this guy receives it, RTB receives it, advertised to RTC, then RTC will also return it to this guy. So that way it will form a loop. So in order to avoid a loop within an autonomous system, we put this rule number 3. You cannot advertise a route land through IBGP to other IBGP neighbors. Now, we can do display BGP routing table, and then we specify the particular network whose details we want to see. So you can see that the local router ID is 2.2.2 because we are in RTB. The autonomous system number is 100. We can see that paths available, one, best one, select BGP routing table entry of this particular network. So we can see that we learned this from router 1.1.1 on the interface 10.1.1.2.1. Route duration, next relay IP address, relay IP out interface. So this is simply the next hop, original next hop. But you can see here at the very last line here, not advertised to any peer yet, because RTB is not connected to any router outside the autonomous system. So it cannot advertise this network because it has been learned through IBGP. So it cannot advertise this network to another IBGP neighbor. So that is rule number 3. You cannot advertise a route learned through IBGP to another IBGP network. Okay, so we look at now rule number 4. Now rule number 4, synchronize BGP and IBGP. Synchronize BGP and IBGP. Okay. So in this example, RTA is connected to this network segment. RTA is connected to this network segment. Now, RTA goes ahead to advertise that network segment to RTB. It advertises it to RTB. Now, RTB does not have an IBGP neighbor relationship with RTC, but has an IBGP neighbor relationship with RTD. Remember we said that unlike OSPF, BGP can actually form neighbor relationships with routers that they're not directly connected to. So it doesn't form neighbor relationship hop by hop, router by router. No, RTB here can actually create a BGP relationship with RTD via RTC. But that means that RTC will not know and learn these BGP routes that are being shared between RTB and RTD. Now, when RTD receives that particular route 100, it's going to share it to RTE using BGP again. So that's an EBGP neighbor relationship. Now, in AS300, RTE sends a packet to RTD that is destined to this guy. Now, RTD is directly connected to RTC, and therefore, in order to get this network, it will send that packet to this guy. But when this guy receives that particular packet, it's going to check its routing table and realize, hey, my routing table does not have the route, and I don't know how to reach this route. So I discard the packet with unreachable destination address error. So RTC will simply drop that packet because it is not aware of this network. It does not have it in its routing table. Now, this can cause what we call the black hole problem. where packets are sent to a destination where they are simply going to be discarded and disappear. So this can result into the black hole problem. Now, to avoid this, you have to synchronize your BGP and your IGP. What does that mean? Before a BGP router advertises a route learned from an IBGP neighbor to another BGP neighbor, IGP must know that route. So what that means is this. Before RTB advertises this IBGP to RTD, the IGP or SPF must learn about this route. It must learn about this route. Because once it learns about that route, then every other router in the autonomous system, because they're using OSPF, is going to learn about their 100.0.0 network. So that is rule number 4, that you have to synchronize BGP and IGP in order to avoid the black hole problem. Okay. Now let's look at the BGP routing information processing. Okay, let's see. So when receiving an update message from a BGP neighbor, a BGP router uses the route selection algorithm to determine the optimal route for each prefix. Then the router stores the selected optimal route to the local BGP routing table, known as the local routing information base, local RIB, local routing information base. So update information received from a BGP neighbor, then find the optimal route and install that optimal route in the local RIB or routing information base. Then submit it to the local IP routing table, IP RIB. So after umeinstall kwa local RIB yako. So that's why when we are doing display BGP routing table, we are simply displaying the content of the local BGP routing information base. When you're doing display IP routing table, we are displaying the content of the IP routing information base. And then submit it to the local RIB to determine whether to install it. So the router encapsulates the selected valid optimal route in an update message and sends it to the BGP neighbor. So whatever is here in the local RIB can now be sent to the neighbor and advertised to the neighbor. Only the optimal, this one is important. Valid, it has to be valid, meaning it's reachable. Then it has to be the best route, the optimal route. So that is how the information is processed in BGP. Okay, so at this point, we want to look at the BGP attributes. The BGP attributes. BGP attributes. Now, the main purpose of the BGP attributes is to control the routes that are selected and to also help to select the optimal route. And as you're also going to see, it can also help in preventing routing loops. Routing loops. Okay, so let's go through this scenario. So in the figure, AS7 has a network segment 100.0.0/24, advertises it to each autonomous system through BGP. So advertises it to all the autonomous system through BGP. Each AS can learn the route 100. However, the following problems exist during route transmission. So let's look at these two problems. Now, AS3, autonomous system 3, can receive the route from 4 and 6. Is that true? Yes, AS3 can receive the route from AS4 and AS6. Now, and the link between AS3 and AS4 has a higher bandwidth. We can see that this link, this one, has a higher bandwidth. It's longer, but it has a higher bandwidth. This one, on the other hand, is shorter, but has a lower bandwidth. So how do you enable AS3 to access the network segment 100.0.0.0/24 through AS4? Because this is the best path. Because it has the highest bandwidth, this is the best path. So how do you enable? How do you enable AS4 to achieve that? So that's the first question, and we are going to get the answers through the BGP attributes. Now, the other problem is there's a loop. There is a topology loop among AS1, AS2, and AS3. So therefore, a loop may occur during packet transmission. So how do we prevent a scenario like this where a loop can occur? So again, we are going to get the answers through the BGP attributes. Now, BGP attributes are normally divided into 4 categories. The very first category is known as the well-known mandatory. Well-known mandatory. Then we also have well-known discretionary. Then we have optional transitive and optional non-transitive. Now, what is a well-known mandatory? Well-known mandatory attributes. Let me see if I can type here. So, well-known. Now, generally, well-known attributes. Well-known attributes must be identified and supported by all BGP routers. Then the second part is the optional attributes. The optional attributes do not need to be identified by all BGP routers. So that's the main difference between well-known attributes and optional attributes. Now, under well-known, we have the mandatory. Mandatory means it must be carried. It must be carried by all routers in the BGP update